Decision tree is one of the popular supervised machine learning algorithm. So as part of this, we'll try to understand what is decision tree and how it works. What are the different algorithms are used to split the tree, decision tree, and then we will take a look at how to implement and interpret the decision tree, and then we will proceed with validating or evaluating the model performance, and also we'll take a look at what is pruning, pre-pruning, and post-pruning. First of all, what is a decision tree? It is a non-parametric supervised machine learning technique. So what do you mean by non-parametric? It doesn't make any assumptions like linear and logistic regression. As for linear regression, logically, you know very well, there should not be any multicollinearity. And in the case of linear regression, linearity should be there. There should be a correlation between the independent and dependent variable. So, the linear regression logic makes assumptions, whereas decision tree doesn't make any assumption. Using decision tree, you can fit both regression as well as classification related trees. It builds classification or regression models in the form of tree structure. It is constructed in a top-down recursive manner. Okay, if you put a tree in an inverted if you put a tree image in an inverted way, right? So how it looks like, that is how the decision tree will appear. Using decision tree, we can classify the instances by starting at the root of the tree and move through it until a leaf node. And what are the advantages of decision tree? Very simple to understand. Even a layman, when he looks at a decision tree, he can also understand and interpret the tree, and using which you can generate the rules. This is very much helpful, generating the rules with the help of the decision tree, right? So we can do it. And also it requires minimal data preparation. It is not sensitive to outlier. And you don't have to do too much of heavy lifting when it comes to data pre-processing. Okay, data type is not a constant. You can use any type of, like a logistic regression, linear regression, all the independent variables are supposed to be numeric. Here, data type is not a constraint. Okay, it requires minimal data preparation. It is considered to be a non-parametric. It doesn't make any assumption. One disadvantage with the decision tree is it suffers from overfitting. That is one of the, but still with random forest and advanced algorithm like random forest, gradient boosted machine, extreme gradient boosted machine, and light GBM, right? It takes care of this one. Okay, so we don't have to worry about the pruning in that case. And when it comes to decision tree, the input variables can be either categorical or numerical. It can be a combination of both. Need not to be in the continuous variable. The output. So once I fit the decision tree model, so what would be the output? Like a logistic regression, it gives you the probability score. It assigns the predicted class label. The other one is it gives you the rules. Generate with that, you can generate the rules. Okay, you can generate the rules like this. If income is less than and mortgage amount is greater than this, then default is going to default with 75% probability. So with this output, the management can take a, so with that they can, so this can drive the decision, the management decision. So whether I can go ahead and approve the loan or not, whether he is going to repay the loan or not once I approve it, or if I give the loan offer to him, will he repay the money or not, right? So based on which, so the output can they can be helpful to make the right decision at the right time to the management. Before we proceed with the underlying principle of the decision tree, let's first be familiar with the terminologies. So if you look at here, this is the decision tree, and here you can see that things happen. So here you can see this is what the root node. This is what called as a root node, and this is called your decision node, and the last one is called your leaf node. This is the these are called your leaf nodes. So in the leaf node, you can see that in the case of classification model, so you will find the leaf node as yes or no. For example, if a customer is a female, And let's say, here's some condition. Our age is less than 45. She is more likely to buy product from our shop. Just by looking at the tree, anybody can gain insight. Okay, so this is my data set. So gender and income, married and buy. So whether customer is going to buy or not. This is my dependent variable. This is my dependent variable. The rest of them are my independent variables. So here gender is female. You just remember in the decision tree, the true value will come on the left side and false value come on the right side. And similarly in this each node. So this is my root node, this is my decision node. In this decision node also, right, the true values will come and the false value come this side. The tree can also have subtree. Okay. So here, if you see the gender is female and let's say income, right? Income is less than or equal to 45,000. Okay. So whether is she going to repay the money or not? Yes, she can repay the money if I give her a loan. If her gender is male and if age is less than or equal to 40, he will not repay the money on time. This guy, people above 40, they are more likely to they are likely to repay the loan amount if you give this one. So with this we are able to quickly understand we can understand the insight, right? We can gain the insight quickly. So this is my root node and this is my decision node and this is my leaf node. And in this case it is a binary classification. If you see under root node, you have only two it has been divided into two partitions, right? The one partition is on the left side, the other partition is on the right side. And even this partition, we can see the decision node, it got splitted with two nodes here. So two leaves here. So in this case, okay, so at each node, so it got divided into two partitions. At this node, root node, two partitions. In this decision, this is called your decision node, right? Below root node, whatever you have is decision node. And then just below this, you can see that this decision node got partition with two leaves here, right? So, but leaf node is the terminal node. So beyond this, it will not grow. Once it reaches the terminal, it will stop. The leaf node, once it reaches, it will stop. So in this case, how the decision tree constructs, so how this model, right? How this decision tree gets constructed. There are three steps here. The decision tree places the best attribute of the data set at the root of the tree. So we have gender, income, married. Of these three independent variables, it considers only gender as the root of the tree. And then it splitted the training set, the entire training set into subsets. Okay, the subset should be made in such a way that each subset contains data with the same value of the attribute. So in this case, gender has been considered as a root node. Now you might be asking this kind, okay, why gender? Why can't it be married? Why can't it be income? Is it because the gender column is available in this data set as a first column? Did it consider as a root node? No, it is not like that. Okay, it is not like that. So for this, we use some, it uses some algorithms like a Gini index or information gain entropy or reduction in variance in the case of random forest. It uses some techniques, okay, to decide or determine which column is supposed to be a root node. So the next one is, yes. So the next, even for this one, decision node, right? So which one should come first? Which one should come next? That one will be driven by those algorithms or techniques, okay, methods. The decision node, this is where we test the value of one feature. For example, if she is a female, the gender is a female and her income is less than or equal to 45,000. This is where we test the condition. If it is true, then it will come here. Okay, if it is true, then the predicted outcome or the label is yes. So here the predicted. So we can find the predicted value in the leaf node. The same thing is applicable for regression, linear regression or regression model. But in the case of regression model, you will, instead of yes or no, you will find the value. For example, let's say the size of the house is less than or equal to something, or less than or equal to 2000 square feet, and the location is some place. Okay, if location is this, then it will come here, and this is the estimated value. Estimated is something like 1.2 crore or something like that. You will find the estimated value in terms of numeric value in the case of regression, whereas in the case of classification, it assigns the predicted class level. And if you want the predicted probability also, that is also possible. Along with this, we can predict the probability also. So we have predict proba function is available, right? So not only yes or no, even probabilities also we can predict it. So using a decision tree, we can predict whether a customer can buy a product or not. Okay, which means we can use decision tree as a classifier, or you can use it as a regression tree. What do you mean by regression tree? Decision tree is a common name. If you try to solve a classification problem using a decision tree, we call that as a classifier. If you try to solve a regression problem using decision tree, we call it a regression tree. That's all. But in practice, they use these two terms. Henceforth, if I say classifier, okay, you should be able to understand. It could be a decision tree, or it could be a logistic regression, or it can be a neural network. It can be anything. Okay, classifier, except linear regression. Linear regression is not a classifier. And similarly, regression tree, if I say, it represents the decision tree. But in this case, we are solving the regression problem. Hence, it is called a regression tree. Okay, now it's time for us to understand the mechanics of the decision tree. I just took the academic example here because you can understand with this super simple data set how it creates the tree. Look here, this is my data set. Okay, and what is the prior probability here? If you look at this data set, we have, forget about the ID, and we have three independent variables: outlook, humidity, wind. And play tennis is my dependent variable. So here, a guy by the name of John, he played tennis with the different possible combination of these, weathers. So when the outlook was sunny and the humidity was high and the wind was weak, he did not play tennis. When the outlook was overcast and the humidity was high and weak, he played tennis. Likewise, in the 14 different times, they recorded the data, right? So when he played tennis, when he did not play tennis, with the combination of these three, possible conditions, okay, weather conditions. So here, if you see how many number of times he played tennis. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of 14 records sample, 9 times he played tennis. This is called a prior probability of playing tennis. Prior probability of not playing tennis is 5 times. Out of 14 times, 5 times he did not play tennis. 1, 2, 3, 4, 5. Okay, now you understood what is prior probability, what is prior probability of yes and prior probability of no, you understood. Now this is the same data set. I just put it here because of space issue, right? I just took a screenshot. It may not be that much clear, the resolution. And when you fit a tree, it will be something like this. Look here in this data set, it considered the outlook as a root node, and then it considered the humidity as the branch node. And then the wind became a branch node for the wind. This is the parent node. For him, this is the parent node. So if the outlook is rain and sunny, if the outlook is sunny and rain, so then there is a high probability that he will not play tennis. If you see no is bigger one here and yes is small here. So if let's take this one, sunny, the sun, rain, sunny, and the humidity is high, and he will not play tennis. Okay, he will not play tennis. And if you see her outlook, rain and sunny, and humidity, okay, so rain and sunny, humidity, and the wind is normal. Wind is normal. Sorry, the humidity, and the wind is weak. The wind is weak. Then he will play. Okay, rain and sunny. Okay, sunny and humidity is normal. Humidity is normal. Okay, humidity is normal. Where it is rain and normal, and the wind is weak, he will play tennis. So with this, we should be able to understand the pattern quickly. Even a layman can understand. See, you can see here, right? So the dark color one is there's higher chances he will play, and there's higher there's a 100% chance that he will not play. There's 100% chance he will play. With this combination of conditions. If the outlook is rain and sunny, and the humidity is normal, and if the wind is strong, and if the outlook is rain, he will not play. 100% chance he will not play. And the wind is strong, and if the weather is sunny, and then he will play. There is 100% chance he will play. Okay, and the other advantage of the decision tree is you can generate the rule here. Okay, the decision tree rule. So in R, we have built-in function. There is something called R programming language. It is meant for statistical purpose, where you can. There is a function called AS rules. With this function, we can generate the rules for your fitted decision tree. And if you see here, this makes your life very simple. If the outlook is rain and sunny and humidity is normal and wind is weak, then you play yes. The probability is 1. There is 100% chance when rain and sunny and the humidity is normal and the wind is weak, then you will play tennis. With this rule, you can understand something which we cannot think about the rules, right? It gives you the all possible combination of the rules. That is the advantage of in generating these rules. Now you tell me, if John play given that the rain, given that the weather is rain, outlook is rain, and the humidity is normal and the wind is weak. Can someone tell me by looking at this tree whether he will play tennis or not? So rain, the outlook is rain. Yeah, rain and sunny come together, right? So it could be rain or it could be sunny. Okay, and the humidity is normal. The wind is weak. Yes, we will play tennis. Very good. No, why you say no, Gilbert? How about others? Jiva says yes. After I said yes, I can see a lot of yes here. So outlook is rain, and the humidity is normal, and the wind is weak. Yeah, there is high probability, 100% that we will play tennis. So there is a predict function that is available in R, even in Python also it is available. And this is the flow, how the decision tree how the tree is constructed. Okay, first it creates the tree, start with the training samples at the root node. In the root node, you will have the training data set, entire training data will be there at the root node. And then it finds the split. What do you mean by split? Of these independent variables, which variable should I consider it as a root? So for that, there is some algorithm is available. So using which it determines which one is the root node, which one is the immediate branch node, everything is determined. And then it grows the tree. And also, right, once it grows the tree, once it grows the tree, our data scientist intervention is required. Right? So you need to prune the tree. Okay, if the tree is overgrown, it can lead to overfitting. Okay, so in that kind of situation, you need to prune the tree. And once you prune the tree, your tree can produce the accurate estimation. Okay, and also you can extract the roots from your decision tree. Now the question is, how does a tree decide where to split, or which column should be used as a root node, which one should be used as an immediate branch node, and so on. So how to decide which feature should be located at the root node? So that is the question now. There are three commonly used impurity measures used in binary decision trees. One is Gini index, entropy, and information gain. Right. So you can use either Gini or entropy and information gain. It can use any one of them to decide where to split. The decision tree algorithm was based on recursive partitioning. Okay, algorithms measure the homogeneity of the subset. Now let us first understand, what is impurity is all about. First of all, let us understand what is impurity is all about. Now let us take the same data set and see here. So the outlook, if you look at here, this is very interesting one. It's kind of a game. Okay, if you look here very closely, and in this data set, outlook is 9 yes and 5 no's are there. So 9 yes, okay, 9 yes and 5 no's are there. So in this case, the root node was outlook. Okay, fine. So here within this outlook, right, sunny and overcast and rain. So how many in the outlook column, how many unique values are there? Sunny, overcast and rain, right? 3 groups are there, right? Maybe multiple occurrences are there, but in total 3 groups are there. In each group, how many yes is there, how many no's are there? If you look at here in the case of sunny, how many yeses are there, how many no's are there? So sunny here 1, and we have 1 second, I'll use this one. Sunny is 1 yes, and then here in this case we have sunny yes, and then I just put something like this. Sunny is no, right? So 2 no is there, and how many? Okay, 1 more no is there. So how many no's are there, how many yeses are there? 2 yes and 3 no's. 2 yes and 3 no's. So this 2 is yes and this 3 is no. Similarly, rain, we have 3 yes and 2 no's are there. In overcast, how many 4 yeses are there, how many no's are there in overcast? If you look here, overcast, how many yeses are there? 1, 2, and 3 and 4. Can we see any other record for overcast? We don't have it, right? Only yeses are there, no no's. We can see here, in the case of overcast, we don't see even a single record marked with a no, right? So yes, only yes is there. So hence, it has a homogeneous subset of the data in it, which means we have only yes. We don't have the mix of yes and no. But whereas here, we have the mix of no and yes. We need to look at the target value in each subset. Okay. And here, so wherever you find no yes, the mix of no yes, this column will undergo further split. It'll undergo, we could see some kind of impurity. If you have the mix of yes or no, we call it impurity. Those nodes that has impurity in it, that one will undergo further split. Since this node doesn't have the mix of yes or no, it is called pure node. It doesn't require any splitting. Okay, since in only these two nodes require split because of impurity, it is doing the further split here. The split this sunny, as the within the look here, it goes back here in sunny, the humidity. So next one is it jumps to the next column, humidity, and in the humidity, so we could see 3 S's, 0 S is there and 3 no's are there. And here we have 2 S and 0 no's are there, which means in the sunny weather, right, and the humidity is normal, 2 times he played. The sunny weather, humidity is high, he never played. All the 3 times he did not play. So here, if you look at this node here, do you find any impurity here? Do you find any? See, if you, by looking at this number itself, you can see here you have 2 and 3. Here we have 0. Of the 2 values, if any one of them is 0, then it's a pure node, right? Same thing here. So in this subset, only high related values are, no only is there. Okay, here in this yes only is there. You don't have the mix of yes or no. You all agree with me or not? See, in this case, we have 4 yes, we did not have any no. Hence, it became a pure no. It doesn't require any further split. Similarly, it doesn't require any further split. It's a homogeneous subset. What is homogeneous? Heterogeneous? Heterogeneous is a mix, right? More than one. Homogeneous, single. It has only no related data. It has only yes related data. It is not having the mix of both. So hence it doesn't require further split. So here also the same thing. So the decision tree start splitting the values, right? It splits the columns from the root node to till the leaf node recursively until it finds the homogeneous subset of the data for each node. Okay. So here we can see that we don't see any mix of impurity. We don't see any impurity. So here, since we did not find any impurity at the first iteration itself, we understood it doesn't require any further split. Whereas in these two subset, we found impurity and it requires further splitting. So after splitting this, it became pure. So this is what impurity, okay? Just keep that in mind. Okay, now we will discuss about something called Gini, entropy, all these techniques. These are the algorithms or techniques or helpful in terms of deciding which column should be considered as a root node. Okay. First of all, what is a Gini index is all about? Gini is an impurity measure. It is one of the methods used in decision tree to decide the optimal split from your root node and the subsequent splits. That is what Gini index is all about. So while designing the decision tree, the features possessing the least value of the Gini index would get preferred. Okay, before that, let us look at the formula here. Gini index. To compute the Gini index, this is the formula is used. Probability of I and probability of J. The sum of the probability of I and probability of J is nothing but your Gini index. And Gini is equal to 1 minus the probability of class 1 squared. We can say this is a class 1, class 2. Okay, probability of class 1 squared minus probability of class 2 squared. Okay, the Gini index of split is Gini is equivalent to Ni divided by N Gini N. So instead of going by this, it will be something like confusing. Okay, just keep that in mind. Gini index performs only binary splits. Only for binary split, you can go for Gini index. Okay, you might be asking this one. Okay, I want to have a decision tree wherein I need to have a multi-way split. Then we have something called shade. We have different algorithm called shade, chi-squared. Chi-squared technique is used in that case. Okay, in the case of binary split, Gini index, entropy, information gain only used. Okay. Also, in the court, it uses Gini method to create binary split. It works with categorical target success or failure. In our case, yes or no. John played tennis, that is success. He did not play, that is failure. So it works only with the categorical target, like a binary categorical variable. That is what it says. And now let us to understand this problem. So this formula, let us work on this simple exercise. Okay. Now, how many classes are there here? How many classes are there here? Only one class is there. How many classes are there here? We have two classes are there, yellow and red. If you see here, we have only one class, the yellow class. But in the yellow class, we have 6 balls are there. Whereas in this case, we have 5 balls are there in class 1. And in class 2, we have only one red ball is there. So I call the class 1 as yellow color, class 2 as red color. So in this case, we don't have a mix of two classes. So class 1, we have 6 and class 2, we have 0. So what is the formula here? 1 minus the probability of class 1 squared minus probability of class 2 squared. That is the formula. So 1 minus class 1 is 6 out of how many number of values are there? Out of the total number of values, how many of them are class 1? 6 only, right? 6 out of 6 squared minus class 2, we did not say anything. 0 divided by out of the 6 values or balls, we don't see any red. Class 2, we did not find it here. 0 divided by 6 whole square. This is the formula. So this 1 squared is 1, and anything 0, anything divided by 0 is 0, right? Sorry, 0 divided by anything, that is your 0 square. Okay, so this is one. Now we are left with 1 minus 1, 0. It has 0 impurity, which means it's a pure node. Similarly here, class 1 is equal to 5 and class 2 equal to 1. So 1 minus probability of class 1 divided by total number of values. 5 divided by 6, 1 divided by 6 whole square was the point. It's a low impurity. And similarly, if you take a look at here, and class 1 equal to 4, class 2 equal to 2. So here, moderate to high impurity. And if you see 50% of class 1, 50% class 3, sorry, class 2, 50% of the balls are class 1, remaining 50% are red color balls, right? So equal split is there. So hence we can see high impurity. So in this case, whichever node has less Gini value, that one will undergo split. Anyhow, this formula is not yet over. 1 second, we need to plug in this one into the next one. So this is just to compute the Gini index value. Now let us look at this one. So this is my root node. In the root node, I have 3 yellows and 3 reds are there. 2 classes are there. In class 1, 3, and class 2 is 3. And on the left side and right side, it's splitted something like this. In this case, after the split occurs, we can see that class 1 only 1, yellow is 1, class 2 is 3. And if you see, it's a pure node. Class 1 is equal to 2. Fine. Okay. So 3, 4, 5, 6. In total, we have 6. 1 second, Mukelan. I'll answer. Let me finish it. So here we have class 1 equal to 1, class 2 equal to 3, and something else. So here, if you see, this is a Gini left, Gini right. Okay. And here 1 minus 3 divided by 4. Here we are total 4 is there, right? Class 2 is 3. 3 divided by total number of values. 3 divided by 4 whole square minus 1 divided by 4 whole square equals 0.37. Similarly, right side you can get 0.25. And you need to plug in all these value into this final thing. The Gini split is equivalent to 4 divided by 6 into Gini left 0.375. So how did we get to 4 by 6 here? And minus 2 by 6. If you see here, this 4 out of 6, okay, that is what the left side says here. And here we have 2 out of 6, the overall thing, okay. 4 out of 6 into Gini left is 0.375 minus 2 out of 6 into Gini right is 0.25. So if you do the math, you get 0.25. Okay. So higher the Gini score will lead to, no, here it is slightly different. Okay. Lower the Gini score, that will lead to split. So in this case, okay, in this case, right, the higher the Gini score, that is the, okay, by after applying this one here, plugging in this one here, higher the Gini score will lead to split. Yes, correct. You are correct. So here, okay. So now let us work on this thing, okay, exercise, so that you should be able to understand. So we have a split on gender. Total number of students are 30, and out of 30, 50 students, they play cricket. And okay, so total in a college or school, 30 students are there. Out of them, 50% only play cricket. But if out of the 15, if you see here, right, so sorry, out of this 30, female students, okay, 10 students are there. Out of the 30, 10 students are female and 20 students are male. Okay, so here in this case, play cricket. All right, so 15. Out of the 15, only 13 students they play, male students, right? Only 13 male students they play cricket. So it goes further split. So total students are 30. So male and female, if you split it, so male we have 20 and female we have 10. And out of the 20 male, 13 play cricket, only 2 play cricket in female. In the female population, 10. So 13 out of 20 is 65%, 2 out of 10 is 20%. Fine. Next, this split happened based on the gender column. Okay. And the next one is class. We have another column called class in the data set. In this case, we have 9th standard and 10th standard students are there. If you sum these two things, 30, right? So 9th standard we have 14 and 10th standard we have 16. And for 9th standard, 6 students they play cricket, whereas in the 10th standard, 9 students they play cricket. So 50, we are able to get the percentage. So how many of the class 10 students they play cricket? How much percentage? How much percentage of class 9 students they play cricket? We are able to get this one from this. Now when you use the Gini formula, so 1 minus probability of class A squared plus 1 minus plus probability of class B whole squared. If you use this, we can find out the Gini for the subnode female here in this case. Okay, I will just tell you the answer here itself. So here the 20%, right? So 1 minus here. Okay. Okay, here probability of class A and probability of class B. For this one, we need to see. Probability of class A is female. Probability of class B is male. So here probability of class A is 20%, which is nothing but 0.2. Class A whole squared, 0.2 into 0.2 plus here if you see the probability of class B. What is the probability of class B here? In this case, we are getting 22%, 0.8. Okay. Here we have taken this one first. I think 1 second. There is some confusion here. I think this guy they did not update it correctly. 0.2 into 0.2 and class B is 0.8 into 0.8 here and 0.65 into 0.65. Okay, this is for female, right? Left side, yes. We are saying, okay. Female, Gini subnode female, 0.2 into 0.2. That means class A is 0.2, 0.2. What is 0.8, 0.8? Let me see how many of you can tell me this one. What is 0.8, 0.8? So 0.2 out of the 10 students, only 20% students they play cricket. Remaining 80% they don't play cricket in the female population. So that's what calculate the Gini for subnode female. You need to understand this one first. Okay, what is the problem here? So 0.2 into 0.2 class C and class B is 0.8 students they did not play cricket. Okay, and hence if you do the math, you will get 0.68. If you separate it from 1, that is the formula. Okay, 0.32. Similarly, in the case of male node, 13 students or they play cricket out of 20, which is 65%. Class A is 65 and class B is remaining 35%. So class is 0.65 into 0.65 plus 0.35 into 0.35 because the formula. Class A is 0.65 play cricket. Yes or no, right? Yes or no. Yes is 65%. This is one class. No is the remaining thing. So you will get 0.55, 1 minus 0.5. So for this, we get 0.32. For this, we get the Gini index 0.45. Now we need to calculate the weighted Gini for split class. So 10 out of 30 into 0.32. So 20 out of 30 into 0.45. So what value you will get it? You will get some value, right? So here, similarly, we need to compute it for the class 9 here. Yes, Mukilan, 0.8 female, they don't play cricket. Yes, that's what I said. So here, similarly, you need to, now you tell me what is the value here, you will get it. Calculate the Gini for subnode class 9. So 43%, means, right, students, they play cricket in class 9, which means the remaining 57 students, they don't play cricket. Okay. And same thing here. So 56% student, they play cricket, remaining 44 they don't play cricket. So two classes are there, play yes or no. In these two things, 0.5 you will get 0.5 and you will get something here. Whichever the Gini value is high, that node will undergo a split for first. So here how much you get it. So okay, let's assume that in this case, right, this node will undergo split. Okay, firstly, that's how it decide which node should go first. So whichever node has lesser Gini value, sorry, higher Gini value, that one will undergo the split first. Okay. The Gini value is 0. That means the impurity. There is no impurity. So right. So then it doesn't require any split. The next one is entropy and information gain. With this, you should be able to get a better understanding. It is a measure of impurity. Like a Gini, even the entropy is also a measure of impurity, and even the value is computed between 0 and 1 in this case. Okay, it is heavily relying on the number of groups or classes present in the data set, right? It can be more than one also, this value. Okay, the next one is the information gain. Okay, information gain is based on the information theory. It is used for deciding or determining the best features or attributes. Okay, and this is the formula is used. Negative and informative, pick the informative entropy. Okay, negative value of probability of class log base to a probability of class. And if you take the same data set and if you apply it here, and if you spend few minutes, you will be able to understand very clearly here. Just spend 3 minutes here in terms of concentrating here. Look here, how many with this already we computed. Forget about the temperature one. Okay, don't ignore this one. This additional column. Okay, outlook, humidity, wind, and plating. You just think this column is not there. Okay, so out of this one, how many we already discussed the prior probability, right? So there is a prior probability of S is 9 and prior probability of no is 4. Sorry, 5, right? 5. 9 out of 14 times he played tennis. 5 out of 14 times he did not play tennis. Okay, 9 out of 14 times he played tennis. If you plug in that formula, right? So into log base 2 of this one minus, so you will get some value. This is the entropy for all the values in your data set. H of S is equal to this one, 0.950. Just remember this, that's all. And here we mentioned number of positives 9, number of negatives 5. In total, we have 14. Fine. Next, we will loop over all the attributes and calculate gain. The first step, and look here, outlook. In the outlook, sunny, how many number of positives are there? How many number of negatives are there? Same thing. The sunny, we can see that 3 negatives and 2 S's are there. Here 1 S and here 1 S. Rest of them are no. So 2 divided by 5. Right. So out of 5 sunny records, 2 of them are having S and 3 of them are having no. Okay. 2 of 5 into log base 2 of 5. Okay. Out of 5 records of sunny, 2 times he played tennis. Out of 5 records of sunny group, 3 times he did not play tennis. So for this, see, only thing is 2 divided by 5. You need to multiply the same by log base 2. That's all. So you get some value, 0.97. Similarly, you do it for overcast. Overcast, how many positives? 4, negative 0. Okay, hence we get 0 here. Okay, and rain. In the rain subset, also we have 5 records of the rain. If you see 5, 3, 4, 5 records are there. Out of the 5 rain, how many times he played cricket? How many times he did not play cricket? So 3 times he played, and 3 by 5, right? So because 5 rain records are there, so 3 out of 5. Instead of saying record, I call it sample. Okay, in this subset we have 5 samples are there. Out of 5 samples, 3 times he played. 3 by 5 into log base 2, 3 by 5. You need to use the negative sign before this. Okay, negative 2 by 5 into log base 2 by 0.975. Okay, we did this math fine by plugging in this value. Okay, now the next thing is, yeah, now the thing is, similarly, we need to do it for other things also here. See, for example, if I attribute humidity, take the humidity, and within this, you see how many number of records are there. Out of the sample, out of that many number of samples in humidity, how many times he played cricket, how many times he did not. You need to find out for each and everything. So in this case, 0.048, we are getting it. Gain is 0.09. If you look at these three columns, look here, the outlook we already computed. The outlook is, 1 second. 0.246 we are getting it, right? 0.246 we are getting it. And how did I get this one? So we have the value for this one, right? For all the cases, what is the entropy? 0.940. 0.940 minus 5 divided by 14. In the case of outlook, look here. So 5. So this is the total number of records. 5 divided by 14. 5 divided by 14 into 0.971. And then what else is there? And minus 4 divided by 14. 4 divided by 14 into 0. And then minus 5 divided. See, for these three subsets within this outlook, right? How many number of records? This is 5 records, and here 5 records, 5 records. So here we have 4 records. Overcast, we have 4 records, right? So, this 0.971 into 5 divided by 14. So 0.94. This is the, this is the total entropy. This is the formula here. So this value minus the 0.971 into total 5 divided by 14 minus this 0, right? So this 0 into 4 out of 14 and 0.971 into 5 divided by 14. Okay, this time one, if you do the math, you'll get gain for the outlook is 0.24. Similarly, if you do the same math for other columns like humidity and wind, you will get some values. So, when you compare all these three values, which columns value is very high? The gain for outlook is 0.246. Gain for the humidity is 0.048. Gain for wind is 0.029. Which one is high here? Which value is high here? I don't know, outlook. Yeah. How about others? Are you all watching movie? See, these three values, which one is bigger here? That's what I'm asking. 0.249. Jiva, 249 is not there here. 246. Yes, 246, right? 246. Outlook. So of these three columns, outlook gain is high. Hence, the outlook column will be considered as a root node. And then the remaining two columns, humidity and wind. Now you tell me of these two values, which one is bigger? Jivanandam. 0.048 or 0.029? Which one is bigger? Yes, 0.048. So hence, this one will go, so this one will be considered root node, and this one will be considered as an immediate decision node or the branch node. And then under this one will go. Okay, this is how it determines which column should be a root node, which column should be a branch node, which column should be a sub-branch node. Okay, you understood? Whichever column has higher gain, that one will undergo split. The same thing is applicable in the case of Gini. Whichever node has, the higher value there, right? So higher value will go that will be considered as a root node. Okay, whichever has the lesser one, that will be considered as the next branch or something like that. Okay. Hope you understood, right? So how the split is determined, right? Which one should be node and which one should be branch? This is how it is determined. Next one is reduction in variance. Okay, this one is used for the continuous target variables. If it is a numeric variable, then the reduction in variances is used. And in this case, the split with lower variance is selected. So we all know lesser the error, better the accuracy, right? So hence lower variances wherever it finds the lower variance. Instead of, see, so far we discussed about higher gain. Higher, the column which has higher gain, that one will be considered root. Even the Gini, whichever the Gini value has higher, that one will undergo the first, that will be considered root node. But whereas when it comes to reduction in variance, lower variance, whichever column has a lower variance, but the formula is different here. That's all. The same thing. If you see the, say, let's take the same example, right? Calculate variance for each split as weighted average of each node of variance. That's all very simple here. The same thing here. Variance for root node here. Mean value is 15.1. So here 30 students are there. 15 students, they play cricket. Remaining 50 students, they don't play cricket. So we have two classes here itself, right? 15 play, yes, 15 no. So we have 15 ones. The SSR considers 1 and no's are considered 0. So, and if you divide this by 30, so this one is 0 actually, 15 by 30 is 0.5. So we have 15 1 and 15 0, okay? This is the variance at the root node, 0.5. And now the variance would be, okay, sorry, this is the mean value. This is the mean value. Next, we need to compute the variance. You remember variance, right? So you need to subtract the mean from each and every value. 1 minus 0.5 whole squared plus 15 times if you do it. And you need to do it for the ones, and you need to do it for 0. And if you do it, you'll get 0.25. Or instead of writing it like this, 15 times the 1 minus 0.5 plus squared plus 15 times 0 minus 0.5 squared divided by 30, you will get 0.25. This is the variance at the root node. Remember this. The next one is mean of female node. So 10 students are there. Of the 10 students, only 2 play cricket. So class 1 is 2 and class 2 is 8. So mean of female node. So 2 into 1 plus 8 into 0, divided by 10, we will get 0.2. This is the mean, and the variance is 2 into 1 minus 0.2 whole square plus 8 into 0. So you will get something. Female node and male node, similarly, you will get something. Variance for split gender for the overall column, right? So here we have 10 female out of 30 students and 20 male out of 30 students. So into the variance for the female node is 0.16, variance for the male node is 0.23. So the total variance for the gender split is 0.21. Similarly, class node, we can find the thing. So of these thing, right, which one, now we need to look at these two. Of these two, which one is having lesser variance? Gender, right? Whichever node has lesser thing here, that one will undergo the split. Okay, above you can see that gender split has lower variance compared to parent node. So the split would take place on gender variable. So lesser the variance, it will undergo split, and higher the gain, right, that one will first undergo the split. Okay. Hope you understood what is Gini index and what is Gini and reduction variance information gain. These techniques are useful in terms of determining which node is the root node, and based on this only the root node and the branch nodes are determined in a tree while it's splitting the tree. Okay,